Right, well, yesterday I was opening locks with a pair of pliers, applying the tension or rotational force to the curtain. And we were looking at how the lock and the pick arm were reacting. But I'm pretty certain the purists amongst us were cringing because I hadn't actually explained why we were seeing those the movement and what exactly is going on. Why are we able to pick these locks? And the answer is quite simple, and I'm sure everybody knows this. It's all down to tolerances. So when these are manufactured, I would imagine the mass production of these levers, they're basically stamped out of metal, and the dies and stamping process, I would imagine they would get worn over time. So a lever 7 produced with a new die and a lever 7 produced with one that's been in production for a while will be a slightly different shape. And this goes for all of the levers, of course. So we can't guarantee that every single lever produced is exactly the same shape. There are going to be very, very small differences between them. And also, the bolt stump on the 2134 is cast as all one part of the bolt works. So again, the casting process has to be absolutely perfect for this to repeat time and time again to get exactly the right shape and position of the of this bolt stump. And I'm 100% certain that over time that's going to change. Different molds, different processes, different metals, different machining. There's going to be an awful lot of differences that will basically all add up to a tolerance that allows us to pick the lock. If the tolerance was absolutely perfect, zero tolerance on these, then it's highly unlikely that we'd ever be able to get the lock open because we wouldn't be able to get anything to bind. But with the errors in the levers and the bolt stump, when we apply the rotational force and bind the lock up or bind the levers against the bolt stump, then what we're doing is we're taking advantage of these differences in manufacturing tolerances and the errors that are introduced. So if we look at the lock, when we use the key, when the key turns, I'm having to hold this, by the way, because the training cover doesn't hold the levers in place. When we rotate the key, you will see that the levers elevate first, and then the curtain pulls the bolt stump through the true gates. So the key aligns everything up. Let's just get that back in place. There we go. The key aligns everything up, and then once everything is lined up, then obviously the bolt stump can pass through the gate. At no stage is the bolt stump actually pulled hard into the side of the levers to bind them. But that's obviously what we're doing when we're picking. So if we put the pick into the lock, let's get the pick wire. So when we rotate this, the pick handle, what we're doing is we're pulling this bolt stump into the side of the levers. And when we do that, the manufacturing errors that I just mentioned come into play because the levers that are closest to this bolt stump will basically bind against it, and the levers that are furthest away will remain loose. So let me get the pick wire. So if you look at the front of the lock here on lever 1, you can see that's not binding at all. Lever 2 isn't binding, they're just loose. Lever 3, lever 4, you can see they're all loose until we get to lever 5 at the back. And lever 5, which I'm just lifting now, was binding. You can hear it click actually there. So what's happened is the side of the lever has rubbed against the bolt stump until one of two things happens. It will either jump into a true gate if it's a low lift lever, because the anti-pick notch is underneath here. So it was binding against this part of the lever here until this became aligned with the bolt stump, and that's what caused the click. Or if we have a high lift lever, let's find a high lift lever. Have we got one here somewhere? Here we go. So you've got a high lift lever here, and then as we lift this up, you can see that the anti-pick notch will engage with the bolt stump first, and the true gate will engage with the bolt stump second. So if this lever was binding, as I lift it up, the very first opportunity the lever has to not bind will be into this anti-pick notch, which is why we get a little bit of a jump when the when the bolt stump moves into this little notch on the side of the lever here. Now, because there are 5 levers in there, the jump back will not be all the way into that notch until all of the levers are aligned in a gate, because what it will do is it will jump into that notch a little bit, but the other levers that aren't set will then start binding. That's why we're able to pick this lever out of its out of this anti-pick notch quite easily while we're setting all of the levers in a gate. But then the moment that bolt stump passes fully into that notch, then obviously it's game over. We then got to back the bolt stump out, release the tension to be able to move the lever up to get the bolt stump into the true gate. So it's a balancing act between the friction or the binding of this bolt stump against the side of the levers, which happens in turn due to manufacturing errors inbuilt inside the lock and the levers, and obviously the bolt stump. So they all interact with each other. So if I pull the bolt stump in, this is the lock that we were picking yesterday. I'm going to just hold that lever in place again. So if we start on the first lever, if you remember when I picked this, we got a jump straight away. So let's just turn that. Okay, I'm lifting the lever now. There we go. So it's just jumped. It's you can barely perceive it, but it does jump. And if you remember, that lever was tapping, and you can see there's quite a lot of free movement in that. What it's doing is it's jumped from that ledge into this gate, and it's now doing that. It's not fully in there because all these other levers are preventing it, but it's just enough. It's an absolute minute fraction for it to be held in there. So if we go on to the next lever, lever 4. So the moment I touched that yesterday, that clicked, and what that's done, it was a high lift lever, and again that little anti-pick notch. The first click we're getting is that just engaging in that little anti-pick notch there, and then what I'm going to do is lift it out of that. So let's do that. So that's lever 5. Let's go to lever 4. So lever 4. Here we go. So lever 4 is bound at that point because of its anti-pick notch, and then if I lift it harder, there we go, it goes up to its true gate. And having dropped into that true gate and now the lever's tapping, it means that lever's loose, and the next lever is able to bind against this bolt stump. So let's move to lever number 3. Okay, so we got a little click out of this yesterday, so let's lift that up. Lifting it up. There. So we get a little click there, and you can see that the levers are just starting to line up here in the back of the lock. So we've now got lever 5 is tapping, 4 is tapping, 3 is tapping. So what they've all done is they've all slid up against this bolt stump until they've fallen into either their anti-pick notch or the true gate, and we've worked that out. And then let's just pick this last lever, which is the one at the front, and you can see I'm lifting it, You can see that it is actually binding here, right on that corner. That's the pinch point at the moment. And the moment it gets beyond that, there, come on, there we go. The moment it gets beyond that, then the lock will then open. So now, obviously all the levers have lined up, nothing's binding anymore, and so of course the bolt stump can pass through the lever pack. But that is fundamentally why we can pick these locks, because of these errors in the manufacturing, or the lack of tolerances, or the tolerances that the differences basically between one lever and another, and one component and another. They all conspire to allow the lock to bind and give us the feedback that we need to be able to understand and pick the lock. Right, well, in true Blue Peter style, I've set up the same tension mechanism we had yesterday with the pliers, but I've extended the arm out here, and I've got a piece of cardboard behind, and I'm using this pick as a pointer, and I put a mark on a starting mark on this piece of cardboard, and with a bit of maths, we should be able to work out each time we set a lever and this drops down, we should be able to work out what the tolerances are inside this lock, how much of a discrepancy there is between the first lever and the last lever. So let's pick it like we did yesterday. So we're going to click on lever 5, rotate lever 5. Okay, so that's the first lever set. Let's put a mark on the piece of cardboard. Let's set lever 4. So that's lever 4. That's gone into its anti-pick notch. Let's put another mark on there. And I'm now going to pick it out of that. There we go. So lever 5. Might need to give lever 4 a little bit of a helping hand here. There we go. So 5, 4. Let's do lever 3. So that's lever 3 set. And again, we've got a little bit of movement here, so let's put another mark on here. So that's 5, 4, 3. Let's just check those levers. 5, 4, lever 5, lever 4, lever 3. So they're all in their gates. Okay, so now when I touch this last lever, sadly the lock is going to open. Let's do it anyway. Just lift that lever 1. There we go. So the lock's opened. But if we have a look at the marks on the piece of cardboard, you can see each time a lever set, there was a movement. And this was the movement that we were detecting and using for feedback yesterday on establishing whether the levers are set or not, and whether they were in their false notches or true gates. But you can see there's actually a perceptible movement there, and that's what you're feeling in your hand when you're picking. Okay, well, maths isn't my strong subject, but from the centre of the curtain to the tip of my point, it was 187 mil, and we had a total of 5 millimeters of deflection from locked to unlocked. So if we use the circumference 2 pi r, 2 pi 187 mil, we got a total circumference of 1175. 1 degree of rotation is 3.264 millimeters, and we had a total rotation of 5 millimeters, so that's 1.53 degrees of rotation. That's the amount of movement that we had at the tip of our pointer. 5 mil or 1.5 degrees of rotation is really small. And in the lever pack, from lever 5 to lever 1, the discrepancy from being bound to not being bound was 0.2 of a millimeter. And obviously without this discrepancy, none of the levers would bind, and we wouldn't be able to open the lock. So picking these mortise locks, these lever locks, is all about exploiting the differences in the bolt stumps, in the stamped out levers, and how they bind against the curtain, and using that to our advantage.